Okay, let us continue. And our colleagues in the two other campuses are online?
Yeah, they are on screen.
In linear, okay.
Yes.
Okay, can you bring up the table, please? Where were we? Oh, let us repeat the steps, okay? What were the 4 steps we have discussed? Step 1. What was step 1? Loud. The phenomena. So what do we want to, we need a narrative. What do we want to model? A narrative. What's happening? And the control volume and the time period. The second step was state variables, right? I don't understand. Perceptual model. Perceptual model, yes. Second was perceptual model. Perceptual model is what's going on. Where's the causality? Third was state variables, correct? So number of people in the room is a state variable. I don't have to model each person individually, but number of people in the room would be a good state variable. And then you can, like Romeo and Juliet, you like the lecture, if you like the lecture, I'm getting encouraged, I speak even better, and your effect, you all have an effect on how I speak, like Romeo and Juliet, and then N could be the number of people in the room, depending on how the dynamics work in this room. So that's conceptual. And then we had, what was next? There is conceptual and the state variables, like number of people in the room, and then what was the 4, the causal factors, which was the causal loop diagram, and we will do this in detail with an example. Now 5, the new step is 5, functional relationships. Now we can model dynamic processes by different kinds of models. There are black box models and neural network models and different kinds of models. The kind of model my personal preference is, but it's my personal preference, other people do something else, is differential equations. Right? A differential equation. The nice thing about the differential equation, it's transparent. You see what it does. When you have an equation, you know what is the variables, and then you can look at the equilibrium conditions. That's why I personally like differential equations. But there are also other models that can be done, and other people in sociology do not use differential equation, but other, which is fine. But mine is differential equation, and I will write down a differential equation. So typically they have the form of a balance equation when x could be a state variable, dx on dt, what is that? What is dx on dt? What's that? The time change of x is the number of people in the room. If dx on dt is positive, what would that mean?
That increases people.
We have more people coming in. dx is negative, people are leaving, okay? And then this is a function of something. Okay, now you look at the loop diagram, right? The causal loop diagram. We had, remember, it was students, myself, and Mario, and Susanna, right? And then you remember the arrows? What was it? Like that, right? And was there an error or not? I don't remember. No error. Okay, So this is the causal loop diagram. And then we have, okay, apologies, Susanna, I'll M. I use M because S is for students, right? So I define 3 state variables, degree of happiness. Okay? If M is large, each of these are very happy. If it's negative, very unhappy. And 0 is kind of average, neutral. Okay? Okay, so let's start with yourself. Your change of happiness depends on what? The only thing you need to do now, we have already the causal loop diagram. We only need to implement the causal loop diagram into these equations. Right? The conceptual work you already did before. Your happiness depends on what? On G and M. Okay, then next, Mario and Suzanne. It's another function, right? Function 1, function 2. And the happiness of Mario and Suzanne depend on the students. Isn't that wonderful? Okay. Good teachers. My happiness depends on S also. Okay, so what we simply have done here, we have transcribed the causal loop diagram into differential equations. I've made an assumption. We've made an assumption that we could also write instead, S is a function of the other two things, right? It would be an algebraic equation. But I've written down the change is a function of the other things. It depends what kind of process we are implying. Sometimes the change is a function of something else, and sometimes the variable itself is a function of something else. Depends what it is, right? So, for example, would you say that the change of velocity with time is a function of gravity, or would you say velocity is a function of gravity? What would you say? Would you say, what would you prefer? It's physics, of course, it's easy. These things are harder, but just to understand, would you say dv on dt is a function of gravity, g is gravity, or would you say v is a function of gravity? What would you rather say? Newton's law. What does? Well, when you drop an apple, then the change in the velocity with time has to do with the gravity, with the acceleration of the Earth, right? So it's the first equation is the correct one. We know in this case because this is Newton's law. It's easy. In the sociology case, we don't know, and sometimes alternative models are okay. There's not necessarily one model preferable or the other, but you can say one is more plausible, or one fits the theory better, or one fits the data better, right? But we should not necessarily exclude one or the other model. Okay, but here, of course, we keep the first one. Okay, we've written down differential equations. Based on universal laboratory relationships like Darcy's law. Darcy's law, is this a differential equation or not? Or an arithmetic equation? Differential. Well, it depends how you write it. You can say usually write it, the change in the potential with space is proportional, the change in the energy with space is proportional to the flux, right? It's a differential equation, yes. Okay, good. So balance equations are a good thing. Balance equations imply additive relationships, dimensionality arguments. They come in very soon. We have a wider range of equations, additional guidance, etc. Okay, so we have step 5a, because we have written down ds on dt, change of the student's happiness with time is a function of the two teachers groups, etc. But now we need to make this more specific. We know s is a function of these two variables, but we do not know what function it is. If we have this law, it's easy because we can just write it down, or Newton's law, or things in physics, or even chemistry, stoichiometric relationships, like how the chemicals change in the aquatic solution. Then it's easy. In sociology, we can also use sociological models, or economic models also, we can do that. If we don't do that, we need to come up with our own relationships. Okay? So, now I would ask you to be creative. I want you to suggest equations for these F1, F2, F3. What functions are these? Would this be, I give you a couple of possibilities, right? Would you say, for example, F1 would be G plus M? Or would you say F1 is G times M? Or F1 is G divided by M? Okay, do you understand the differences between these two things? Or we can do G minus M, even better. No, M minus. I want to be polite. You understand the implication of that? Okay, I have given you 4 choices. Okay, you are engineers, you can understand equations. What are the implications of these 4 choices of F1? I would like to know a narrative for and rationale why we would choose one of these 4. What do the equations do? Can anybody explain? Okay, I'll explain the first one and you explain the other 3. So the first one says, if Günter and Mario and Susanne are happy, then your happiness increases proportionally. Okay? Option first. So, option 2. What does that say? G times M. Option 2, yes?
It says that your happiness and Mario happiness, they are only one thing because we have
a product?
Times, because it's you times
It's a product,
Mario.
yes?
So if Mario is unhappy, probably you will be unhappy and we will be unhappy because it's a time. So for example, if Mario happiness is 0, our happiness will be 0.
Okay, let us first define what is the range of the variable, so we are not confused. So we have 2 possibilities. We can allow these variables, and I would allow the 3 variables, SGM, to vary in the same range. Why not? For symmetry. So we have 2 options. From 0 to infinity, or from minus infinity to infinity. Or from 0 to 1, you could say maybe 0 to 1, or from minus 1 to 1. Or, right? So what would be your preference?
0 to 1.
0 to 1, okay.
I think minus 1, because we can be unhappy.
Yeah.
Depends how you define it, right? You can say anything less than 0.5 is unhappy. Yeah? 0 to 1 is usually a very good choice because it makes it non-dimensional. But we are free. We can also minus 1 to 1 if this is your preference. Why don't we say -1 to 1? So anything that's negative would be unhappy in different degrees, anything that's positive up to 1. And 1 is perfect happiness, right?
Yes.
We never can reach it, but 0.99 after the course. Okay, so the range of SMG is from -1 to +1. Okay? Good. Now, with this definition, you need to reconsider what you just said, right? But we were not, it was ambiguous because we were not clear about that. Okay, please.
On equation 2, we say that our happiness, if one of you is unhappy, we'll be unhappy too.
Your happiness will decrease.
Yes.
Your happiness will decrease.
Decrease, yes.
Yes.
Because if you have a -1, we'll be negative because
Yes.
we have times.
Very good. What about if we are both happy? It's best for you.
Yes.
What if we are
Students
both
will be
unhappy?
Students will be happy.
Okay. Yes. This is what the equation tells us.
Yes.
Precisely. Okay? Just you understand what the implications are. Very good. Now, who would like to do the third one, the ratio? Who would like to do the ratio? And the negative signs are funny, right? They do funny things, particularly if multiplied. Who would like to do the ratio? Yes?
The third equation says that the more Mario is happy, the less the students will be happy. Because the denominator increase means the result decrease.
So it's a bit tricky one. Let us assume we are both reasonably happy, positive, right? Let's just look at the positive case. With the negative case, then we have a similar relationship as before,
True.
right? But let's just look at the positive case and optimistic. What will happen? If Mario and Susanne are more happy, your happiness will not increase so much, right? Yeah. Okay, very good. And with the negative case, it's similar with the product. Last one. Who would like to do the last one? Who would like to do the last one? Yes? Very good.
And our happiness will increase just if Mario is more happy than you. So
Very
if you
good.
are more happy than Mario, our happiness will decrease.
Very, very nice way of putting it. Yes, you're jealous. Okay, good. So there's more complex relationships, but for you to understand what an equation means, for engineers, we need to know that, not just in a sociological context. Good. Now, what's your choice? You're all nice people. You go for the first one. Okay. Second one. What about Mario and Susanne? We have a number of options. We could say, okay, again we have a number of options. Same rationale, what do you think? Any comment? Anybody who would like to comment? Yes, please comment.
The first one is proportional. So if we students are happy or unhappy, the same with Mario and Suzanne.
Okay. Which is your preference out of the three?
So I think first one.
Okay. Okay, what about the last one? Okay, then you get a differential equation, which looks like that, just for you to understand what your decision now was. And the decision is now disaster. You will see in a second what you have this, not equilibrium. Okay, there are two observations. The first observation is the form of the solution. And then there's something else I would like to discuss, which is very important for building this kind of model. Okay, can you give me the solution to this, set of equations? What will it look like? Just by reasoning. Okay, S increases, M increases, G increases, everything increases exponentially. What will happen? We will hit 1, right? Within a couple of hours, everybody will have the perfect happiness. And what do we do if it's 1? So the limiting behavior is not satisfied. The solution of that, if you draw the, this is time, this is S time M G. So we start from happiness of 0. We'll go up like that, very boring. And then we hit 1, in which case the equations are no longer valid, right? It's an unstable situation, just goes up forever. In reality, there will be some counteracting forces that don't allow you just to reach 1 or go beyond 1. So a good equation will be built in a way that you cannot exceed 1. This you can. Okay, that's observation number 1. Observation number 2, what is the unit of time? The units of time, what is it? Seconds, yeah? Seconds, right? So, what do you think about these equations? You're engineers. You should already have cried, no, you cannot write down this equation. Why? There's a problem with these equations. You see the problem? There's a problem with these equations. What's the problem? There's a dimensional problem. You see the problem or not? No? Like the equation is waving a big red flag. No, I'm wrong, I'm wrong. With the physical equation on the left and the right-hand side of the equation must be the same dimension. You cannot have on the left-hand side meters and on the right-hand side kilograms. That's just wrong. It's not that it's wrong. You cannot do that. It's not a good idea to do that, to violate that, right? It's very basic. This is what you were going to say, or would you like to comment more? Please.
The right side is not related to the time?
Yes. So if SM and G are dimensionless, which probably would be a good idea, the dimension on the left-hand side is time to the minus 1, right? Because it's divided by time. And the dimension here is 1, because it's dimensionless. That's not possible. So what do? We are problem solvers, right? We're not problem makers. How do we solve the problem? Very good. Exactly this is what we do. We add a constant. So we can add a constant here. So does your happiness increase to the same degree with Mario, Susanne's happiness and mine? Or would maybe their happiness be more important for you? I'm leaving in 3 days. Just consider that. Okay. So what we do here, we can add a coefficient. We call it maybe I use, for coefficients, I use Greek letters, but other people do something else. I can use psi 1, or not better is psi g, and psi m. This is a Greek letter, it's a constant, 0.3 for, no, not 0.3. What's the unit of this constant? What's the units of this constant? No, not time. Per time. The unit of that is per time, time to the minus 1. Per time. And here we also need a constant, right? We call it perhaps phi s, and here we call it sigma s, right? Just whatever letters, right? And they all have units per time. It has to do, the inverse of this coefficient is called a relaxation time. When you have an exponential decrease or increase, this can be fast or slow. It tells you how fast does your happiness increase with the happiness of the others, right? This is the time constant, a constant. Now we have the relationship. With these dimensional considerations, now it looks like a limitation, but really it's a very good thing, because if you have more than one unit, if you have kilograms, dollars, meters, right, degrees centigrades, you have different dimensions, and dimensional analysis helps you to arrange the terms in a way that they make physical sense. It's called dimensional analysis. It's a very good theory, dimensional analysis. Helps you arrange the variables in a way that they're physically meaningful. Okay? You have a doubt? Yeah, please.
A component can interfere in herself. Like, for example, the happiness of the students also depends on us. For example, if I'm sleepy, if I'm hungry, this can happen. I have an arrow to myself.
This is a very good comment. This is actually something I forgot. Thank you for pointing that out. What about, why didn't we include S here? And why didn't we include M here? And G here? Right, this is what you're saying? In the loop diagram, you could indicate like that if you wanted. Some people like it, I don't like it so much, but this is right. The state, the change of your happiness can depend on your degree of happiness. That's actually a very good idea, and this can help us to avoid the problem of exceeding 1. Right? You can use your M, your own coefficient, your S, in a way that automatically 1 is the upper threshold. Okay? If you let us try it out, what it should look like, the equation. You need to make a little space. Okay. Let's only do this equation. I want you to refine this equation in a way that it never exceeds 1 and never is smaller than -1. Do you understand my question? Currently, it can go up to infinity, but I would like you not to go up to infinity. So currently, it looks like that. And we want to expand it in a way, so it's psi g times g plus psi m times m. Okay, this is the current version. And of course, it will explode. But can we do something that it will not go beyond 1? How can we do that?
One divided by it will never explode.
We can do 1 divided by that, that's a possibility, but then you will get the effect that your happiness decreases with my happiness. If this is what you want, it's a possibility. Another possibility is to introduce something in a way, S in a way, that if S is close to 1, this term goes to 0. So we could, for example, say times one minus S. It is not perfect, it's just for this end, but just for the argument's sake. Okay, if S approaches 1, what will happen with this equation? So the change in time is 0, meaning what? It will not go above 1.
Could you please use these 2 pens because people are complaining that they are not able to read the report.
Okay, yes, thank you. Will do. So where's the cap here? I will use these 2, okay. Okay, so if I introduce this term 1 minus S, S will never go beyond 1. You understand why? Because S we're starting from 0. As it goes up, it gets stuck at 1. It may go down, but it will never go above it. Now we not only have included S as a dependence on itself, but also as a way to limit it at 1, which is a nice limit. It doesn't work for -1. We need to think how to do that. And that's why people usually do between 0 and 1, because then it's easy to write. There's no difference, just a little simpler. Okay. Okay. If I have if the equation looked like this, what would it look like? What's the solution to that equation? This is an ordinary differential equation, first order ordinary differential equation. It's the simplest non-trivial differential equation you can think of. Simplest. 1 variable. Ordinary, not partial. What's the solution to that? It's close. It's an exponential decay. Exponential decay, right? So the solution to that is e to the minus t is the solution to that, of this equation. For example, when you have radioactive decay, this equation, this is the solution, proportional to that, of course, right? Okay. So we have the equations. Are we finished? Step 5. We were with step 5. Narrative, translate the narrative into cause effect. Use local data, maybe guidance by the implications for the system dynamics. What you can do with this equation, you can find the equilibrium solution. Let's do that. What is an equilibrium solution in dynamic modeling? Equilibrium solution? Okay. Let's take this equation. Let's take this one. The solution of this will look something like this. This is time and this is S. But if the equation were more if we had like a stochastic term, the solution may be more different. So it may look like this with time. Not this equation, but generally speaking. And now, if the forcing, if the input does not change with time, so if there's no time change, what will the solution look like? This is called the equilibrium solution. And we find the equilibrium solution by putting this to 0. If we say no change because it's equilibrium, there's no change, it's constant. What is the situation in a dynamic system when there's no change in time? When you go to sleep, for example, there's no change in time. Your happiness and unhappiness will not change, right? So how do we find the solution to the dynamic system? We set the left-hand side to 0. And then we find the condition under which equilibrium occurs, which is a nice way of analyzing these dynamic equations. And we do this here. So 0 is this, and then we find G is equal to minus. If this is 0, then this is the equilibrium solution. You will be in a state of constant, unchanged happiness if there's a balance between the happiness of Mario, Susanne, and myself. So that's the outcome of this equation, if you believe these equations. Okay. That was step 5. Now let's on to step 6. Now we can solve the equations. How can you solve differential equations? How do you normally, in your daily work, how do you solve differential equations? You're not doing it, are you? I was kind of joking. So if we were to, if you attend a social hydrology class that doesn't run over 3 days, but over 3 weeks, your teachers will make you solve these differential equations. Do you have any idea how you could do it? How can you solve differential equations? You have heard mathematics, right? Calculus. Did you learn about how to solve differential equations? I'm sure you have. Engineers know to do that. Should know that. But in these days, we don't do it manually anymore. Do we? No, it was 20th century, 19th century. How do we solve differential equations now? There are 2 possibilities. Analytically, using software who does it for us analytically. Plug in the equation, and if it can be solved analytically, many cannot, just the simple ones can, will pop up the solution of the particular solution of the equation. One way. The other way, you can simulate it. You put the equation into a piece of software which allows you to vary the boundary conditions. For example, in hydrology, time variability, the boundary condition is often rainfall. So if it rains a lot, there will be a flood. If it doesn't rain, there will be a drought, or it could be pollution, right? Or the input could be the oil price or gross national product. It changes with time. And a solution of the equation that changes with time, you cannot do this analytically. You know, do this numerically. Any idea what software you could use for that? Have you used any modeling software? Have you learned programming in your studies? What software? MATLAB, yes, you could use MATLAB. Any other software? Python, very good. Third one, which is quite popular in my group? R, right? So Python, MATLAB, R, and there is an open source, software of MATLAB. It's called Octave, which is very similar to MATLAB, which I use in my courses. Octave, it's free. It's very similar to MATLAB. Most people use R and Python, which is also free. Okay. So you plug this equation into your program. You need to program it properly, but you don't have to really think how to solve it. Just write it in the appropriate form, and you need to input the files for the boundary conditions that you can solve the differential equation. You get a time trace like this one. Okay? But we forgot something. What did we forget? we forgot something. If you plug in an equation with coefficients, you need to specify the coefficients, whether it's 0.3 or 0.7, otherwise you will never get the result. Okay? How do we choose psi, these coefficients? No.
I think that putting boundary conditions.
Okay. Now in a differential equation, in a dynamic differential equation, you have initial conditions, a starting value. In a dynamic, which time dependent, where time is the independent variable, you have an initial condition, how you start. Do you start with a lot of happiness or without happiness? You need to set at time 0 S to a certain value. That's called the initial condition. Okay, if you do not have a dynamic differential equation, but a spatial differential equation, it goes from left to the right. For example, the heat propagation in a rod. You have a rod, you heat it here, and then you calculate how does the heat propagate along the rod. It's like a simple physical problem, which is different differential equation. It's a diffusion equation. So you need a boundary condition. You need to keep the heat here constant, or the flux constant, and on the other side also. That's a boundary condition. A boundary condition is identically the same thing as an initial condition, but in space. The difference is, initial condition you only have one at the beginning. Boundary conditions you can have two, depending on the type of the differential equation. Some only need one, some need two, and some need more depending on the order of the differential equation. Okay, why do you only need one initial condition, but often two boundary conditions? Why? Space and time is symmetric, isn't it? Is space and time symmetric? What's the difference between space and time? Philosophy, physics. What's the difference between space and time? Or is it exactly the same? If you look at the wave equation, you will see it's very symmetric in space and time. Many equations are very symmetric in space and time. What's the difference between space and time? Okay, I tell you. In space, you can go back and forth. Works, you see? Okay, now you do the same in time. You cannot. Time always goes in one direction. And the interesting thing is that Newtonian physics, the classical physics, does not tell us. So Newtonian physics could go back and forth in time. But we cannot, because there's something else beyond Newtonian physics. Entropy, thermodynamics, and entropy tells us you can only go in one direction. You cannot go against the time arrow. Okay, and in novels you can, but in reality you cannot. That's why it's not perfectly symmetric, and that's why we have one initial condition and often two boundary conditions. Okay, so no, but coefficients are not boundary conditions. That's a different thing. It's not the same thing. Coefficients is different. Generally in modeling, a model is composed of two main bits, of two main parts. One is called the model structure. The model structure is, and I will rewrite this here in order to let us remove this. Cancellino. Okay. Okay, so the model structure here in this equation is everything that is red. That's model structure. That you have a time derivative, that you have g plus m, that's model structure. It's one component of the model, of the equation. The second component of the model is the coefficient, the blue things. They're two separate entities, and generally The modeling philosophy is for generally, not just in hydrology, or everywhere in models, mathematical models, in the natural sciences, in the sciences in general, really. The model structure is supposed to be universal. Universal. The model coefficients are case-specific. For example, if you write down the deflection of a beam under a load, right? The deflection of it, you understand? The equation for that, just by integrating the elasticity theory, will be the same everywhere, whether it's steel or concrete or wood. Same equation, no difference, as long as it's a thin rod, right? It's a thin beam on two supports. Same equation, but the coefficients will be different depending on whether it's steel or wood. The elasticity will be different. That's a coefficient. Okay, so we have two parts in models, and doesn't just apply to socio-hydrology, but generally. Model structure, which is universal, supposed to be universal, and model coefficients, which are case-specific. So we need to get the coefficients for a particular case. That's the idea. Okay, how can you get them? For this model, that's your happiness is a function of the teacher's happiness. How do you get the coefficients? Xi G and Xi M. Any ideas? It's your task now to find the coefficients. Units per time. Okay, who has a guess how to do that? For this classroom, right? For today.
In this case that you have only two variables, you have to have at least 2 points null of your system.
Yes.
So you have to test, like with Günter, with this happy for Günter and this happy for Mario and this happy for the people, for the students, and then test another thing, and then you can settle your coefficients.
Yes. Very good, very good. So we make an experiment. Just think about it, right? Okay, we make an experiment. So we need to, usually social scientists do this by a questionnaire. You understand? A questionnaire, asking questions in a written form, a questionnaire. So they design questionnaires, and they are very good in doing this, much better than engineers. So they write a questionnaire, and then the questionnaire is presented to Suzanne, and she needs to fill it in. What is your happiness, right? And then to you, collectively, and then we accumulate it, and to myself. And we can repeat this for different states of happiness. It could be a self-assessment, how happy I consider myself, or it could be an external assessment, which is usually better, because some people cheat, right? They don't say the truth, right? So I could either ask you, please fill in the question, or a button, you know, electronic. You could vote on your smartphone. You know, there new software when there are these kind of meetings, and then you get a link and you can vote, right? You have seen that? Super convenient. Okay, you can vote. I make you vote about your happiness, which is a self-assessment. And of course, Suzanne and I could do the same. Or alternatively, external assessment. I can look at your eyes and say, well, this one, he's really asleep. He was not very happy. But I like the glow in your eyes. You are very happy. External assessment, which is probably not very accurate, right? But also the self-assessment is not very accurate. So we need to make this experiment in-house here. Will take us 2 hours maybe, and then we get data points, and then we can fit these coefficients, as you said, in a way that our data points are fitted. Okay? You're happy with that? And if you repeat this experiment in Vienna, in Austria, in half a year, you will get different experiments because they're different people. Okay? Which is fine. And the model structure may still work. Okay, so this is how we get the coefficients. Let us see what the table says. Okay. Very good. Now you have a model, and we can solve it now, just with this software, and then we get a result. This is the result of our model as a function of time. And now I'm asking you, or a water manager will ask you, okay, I'm your socio-hydrological model is very interesting. I'm really impressed by the mathematics. But I have no trust in it. You just made it up and it's probably wrong. What will you say to that? Will you say, yes, I made it up, I'm sorry, apologies, and you go away? Or will you try to defend it? What will you say about it? Okay? As engineers, the managers need to trust in us. They need to believe that what we're doing is right. And we have all sorts of strategies. We have good theories and transparent procedures, protocols, norms, engineering norms. People trust us, society trusts us. So this is a new model. What would you respond to the water manager, Ricky, if he or she doesn't, it doesn't say, well, maybe it doesn't say it's wrong, but they say, how can I have trust in the model? You can prove mathematically. Can you elaborate? Okay.
I can't. No, it's just that.
We need to validate our model with different situations and tell him that it works.
Okay, very good. We play a role game. Okay, I'm the manager. You are the developer of the now you. Okay, very good.
We change it.
You developed it together jointly. That's fine. So you developed the socio-hydrological model. You need to convince me, the manager, water manager, that your model is reliable because you want to make money, right? Okay, so I'm saying, well, your model is very interesting. I never knew that you can actually put the behavior of people into equations. Always thought it's only physics you can put into equations. And why do you think this is representative of our water management situation?
We need to tell him that we test...
I'm the water manager.
Yeah.
You are the modeler.
Okay, so I test the equation and the model in different situations and it works.
Okay.
So I validate my model.
You tested the model in different situations and it worked in the situations, and I can assume that it will also work in the future. Is it what you're implying? A water manager wants to work in the future, right? Because you make planning for the future, right? With the past is interesting for scientists, but for the manager, they do work for the future. So are you saying that because your model worked in the past, you think it also will work in the future? Is it what you're saying?
Yes. The data that we use to build the model is just the past. So
yes. Of course we are saying that because we're doing it all the time. You know, yesterday I observed that the sun went under the horizon and came up in the morning, right? And my prediction is same will happen tomorrow. You agree? I'm not sure, but happened in the past, thousands of years, probably will also happen tomorrow. We always base our predictions on the past. Okay, so that's a good comment. But then I will more subtly. Well, do you think your classroom situation of asking the teachers and the students is representative of a real water management situation? You need to say yes, you need to convince me. But how can you convince me? You say no.
No, I don't know.
You can use past situations that really, you can ask for real situations that really happen in the water system, and then hide the information for the model, and then put the model to work and see if the answer is similar to what happened.
Okay, you've got it? She put it very nicely. I repeat it, but you said it very, very clearly, very nicely. Look at the real world situation that is comparable, hide the results, measure them, but hide the results, apply the model, and then only after you have applied the model, show the results and compare them with what the model did, right?
Yeah.
That's called validation. That's a very good thing. So when a manager sees, you have validated the model, I think I can trust the model. There's also another consideration if managers trust models, because they trust the modelers. For example, many of the projects I'm doing, about half or 40% of the projects I'm running in Austria are applied projects for the water industry, for the government, flood estimation and droughts and climate change and all sorts of things. The other half is fundamental research, right? Science foundation research. But for that half, the main reason why I'm doing that is because the water management know me. They have known me for 30 years. In the past, I've never let them down. The models always worked in the past 30 years because they were my models, right? So testing the model is very important, but often you need to show a track record of successes. Not just myself, but every company. You know, a company when you go to the consulting companies, they always show a list of reference projects. The project that I have done in the past and were successful, right? So it's also the person that the manager needs to trust on. And the reasoning is, well, this is a very good modeler. Her models worked very well in the past. They will also work very well in the future because you know how to model, right? So this is a second reason, both reasonings, validation of the model and trust in the people. And we can do uncertainty analysis, sensitivity analysis. We play around with the inputs and the parameters, and then we see how much it varies. It's easy to do. Most people do it. It's not a bad idea, but the other two things are the more important things. Okay, step 7. Now we're finished, right, with that? How do we do time-wise?
You have 30 minutes.
How many? 30 minutes. Okay. What's that?
25.
25, good. Okay, now we have the 7 steps. What do you think? Should we now, we have now 2 remaining things to do over the next 2 days. Not 2 days, really. We have 2 more units, right? This is the 3rd unit, there's this unit and 2 more units. I'd like to apply this with examples, and then maybe towards the end, how to use them more specifically for flood or for water management. But I suggest we start with an example, right? But then I need a selection. I would like just to do 1 or 2, start with 1. And I also need volunteers, because now I've been talking for hours. Now I want you to talk, you to explain that. I want you to apply what I've been teaching in the past hours to your case. It's your problem. You will solve it in front of the classroom, okay? You're nodding because you're thinking somebody else is doing that, correct? I understand. Okay, how do you want to make the selection? You can roll a dice, we can draw numbers, I can appoint somebody. What is your preference for the selection process? Or volunteers? There's always a number of ways to proceed, right? So the trick is when you chair a meeting, you moderate a meeting. This is now, it's not sociology, but just for social skills, right? Soft skills. I'm chairing the meeting. Yeah? I'm the leader of this meeting. Before I make a decision, I ask for your agreement. So it was very clever what I did, because I did not appoint you, but I asked you, how should we appoint somebody? And then let's say, let's draw a number. Right? Or I say, I put a letter on the whiteboard, and whoever's name begins with this letter needs to come out. But before deciding that, I ask you, are you in agreement? And of course you are in agreement because you think it will not be me, it will be somebody else, okay? Then you're in agreement, and we do it. Then there's no problem with myself. You decide it. You understand the trick? It's very clever. This is what you should do, because also the group generally is happy with that, right? So this is a good procedure. Okay, how have you decided? How would you like to make a selection for volunteers? We can have these 7 steps for the problem, different people. I don't want one person to talk all the time, but somebody needs to make a start with the phenomenon, and we need to select one of these examples. Who volunteers? Maybe that's, you raised the hand. No. Just, okay.
Can we work on groups?
We can do group work, but I would really prefer to have it here in the classroom, because in the process of going that we can discuss it, right? Group work is very good if there's more time. Like if we had a couple of days in the PUB predictions in Engaged Basin Summer School, I'm running in Vienna in July, we have a full week, then we have small groups, also the social hydrology school in China, 6 weeks, small groups, right? It's not enough time, so I prefer to, but it's generally it's a good idea.
Okay, I can volunteer
You make a start,
myself.
you're convinced, and then you get the privilege to assist in the decision. Would you come outside? Yes, come outside. Now, the first thing, can you go up with step 1? Because we're now doing step 1. I clean the whiteboard. So you have a microphone?
Yes.
Okay, now I want you to take my place. And the first thing we need to do is to make a selection which of the case studies we should now deal with. Okay, can you moderate the process and ask your fellow students which one would be suitable, one that is very clear, that is easy to start with, right? Where the socio-hydrological processes are very easy to formulate, perhaps.
For me, it's my my case study, but this is a democracy. So, if you wanted to start with some other case, it's up to you. Yeah, São Carlos. Okay, so.
So you're the chair, you get an extra bonus. You get, when you're in front, you get an extra bonus over your colleagues because you're standing in front. No, everybody's agreeing with yours because you're brave. You start the process. Very good. So everybody's in agreement with the flash flood. Okay, yeah. Then let's do step 1. And I would like to have this more specifically and maybe a couple of words written down so we remember for step 2. Okay?
Okay.
Narrative.
So, yeah, because this step 1 we already did, but...
More detailed. More detailed. More details.
More details, okay.
Much more details.
Okay, so here in São Carlos, the urban catchment often suffer with floods coming from the drainage and also from the river. And the commercial area that is in the flood risk area. It's a flood risk area, and they don't. The shopkeepers don't want to move, so. This is how is the name when you it's a locking because it's locking because they can move but they don't want to move, so okay, physically they can move but they don't will do it, so and more details. Please help me. What more else I need to say about the case? What you want to know about?
I think it's important to say that they have a lot of economic losses because of the floods.
Yeah. They already have like some defense systems for the flood, but when it's a biggest event, it's not enough to contain the flood. So usually they have a lot of economical losses.
Why they don't want to leave?
Yeah, in the ask again too.
Why they don't want to leave from the risk zone?
Yeah. In the interviews, they answer that if they move to another place, the shoppers will keep going to that place because people are usually are familiar with that area, and it's like till the moving happen, I don't know, all of them need to decide to go to other place, and it don't will happen. Yeah, they are familiar. They think that they belong to that place, and it's it. They just live with the problem.
I think that maybe they believe if they change the place, if they go to another place, they will have more economical losses because people won't go there. So I think it would be important to show to them which one compensa mais.
Yeah, because for example, after huge flood, less resilient places close because they suffer a huge economic loss, and then they close. But after days or a month, there is another shop there because another person choose to go there, even knowing that it will flood again. And interesting thing is that they don't want to remember. They don't allow us to put marks about the historical floods because they don't. They are afraid that the clients know that these places were flooded. They don't. The people don't will buy stuffs there because it will be flooded products or something like this.
So what about the critical period? There are a critical period of the year?
What?
The critical period. When this happen? Like
critical
summer
period.
or something like that?
Critical period. Yeah. Yeah, in the summer, usually from October, November, yeah, until March, I guess. Yeah. Yeah.
They have also made black enchant.
Yeah, there is a big sale after the flood.
They made a black flood, like Black Friday, but black flood, and the products are all cheaper.
Okay. I don't. Other interesting thing is about the drainage. We don't have data about the drainage. Like just they don't know. The municipality don't know. So it's difficult to model properly the flood that come from the drainage because there is no data.
They don't have a map with the drainage system here in São Carlos.
Yeah.
And I want to say that the fear that they have, that people avoid the place when it starts raining, it's real already. Because everybody that I know here in São Carlos that lived here for 1 year or two that have seen things happening, avoid the center and the area next to the shopping, because we don't have only one place here that suffer with floods. We have a lot of places everywhere where the river pass. Yeah. We have this problem. So it's not like a moving problem only. They don't have even the shopping we have to avoid when it starts raining here.
Yeah. Even the shopping, but the commercial area in the city center, it's in a down part, and it suffer with floods more frequently. But yeah, many other places suffer. It's not one flooding area, but multiple flood areas, not just one. Yeah.
Do you have any idea of how much time do they have to prepare before it's flooded? I don't know if I know it varies, but I don't know a mean value.
I guess it's very fast, like a half hour. It's very fast. Like the time of concentration of the basin, it's 2 hours. But if the flood comes from the drainage, it's like a half hour or less than it. And we don't have any warning system working here also. So. But we have the expertise of the civil defense. So if they look to the sky and say, okay, a big rainfall, it's coming. Okay, it's enough for the...
I think this is okay. Very good. We now have a very good phenomenon, a very good story. I think it's very good. And I think if this is okay, we change to somebody else. Yes? Thank you very much. Yes, put your hands together. Thank you. Now, who would like to be the second star of this evening? We need step 2. Maybe you can recommend somebody to follow you. I think this is a good system. So everybody recommends the successor. So you make friends. So please come outside. No, there's... Okay, so I'll... So very good. Thank you. Micro.
She pointed out an important thing. We don't specify the purpose.
We don't?
Specify the purpose.
Very good. We did not specify the purpose. Okay, what is the purpose? Yeah, very good point. Yeah, we forgot. I forgot.
Predicted the flood to reduce losses? Or test changing scenarios to solve the problem. I don't know. It's to we can do it for solve the problem or to live better with the problem. I don't know which you prefer. Which one you prefer?
We have 2 options. One is to understand the mechanisms. Then we could do sensitivity analysis, change the parameters. Or we could write it down in a way that it optimizes. So you would write it down as objective functions, the losses, and then minimize them, or the gain and maximize it. Right? You can write it down in an optimization framework, or you can also start with just trying to understand, trace the time history. Then once you have that, you can easily just modify this in an optimization module. So my suggestion for purpose, try to understand their mechanisms, the feedbacks. Would you be in agreement? Yeah. So then I complete this here.
I also have.
Purpose, very good point. Are there any feedback mechanisms in this narrative? Second. Are there any feedback mechanisms between water and people? So how people behave, does this change the flood or not?
Yes.
Okay.
There are more people living there in the catchment, so these will generate more runoff.
Because of less infiltration?
Yes.
Okay. Then urbanization, and I should maybe, for the feedbacks, if you want to, you can also do social hydrology model without this kind of feedback, but then maybe it's just an economic model, right? Urbanization. less infiltration. And therefore bigger floods, of course. Okay, thank you very much for this edition. Now the stage is yours. Cesar.
Hi. Well, my case is flood pollution.
No.
No, sorry, I didn't.
Your case is urban flash floods and step 2.
Step 2 from her case.
Yes.
Okay. Yeah. I think we could use hydrological data.
I think, just for illustration, I think it's clearer for you if we use the same case study in all the steps. Would you be in agreement? We could also switch between case studies, but I think we just try to be imaginative, even though you don't know all the details. Let's try to imagine what could be. Let's do step 2. What does step 2 say?
Is perceptual model. So I think we could use hydrological data, because with hydrological data,
yes,
to know about how much water we have, and to help us to predict when the floods will happen. But I think that we already know when the floods will happen. So we could use hydrological data just to predict when is more what is the
runoff,
the highest chance to happen, and we can predict the level of flood.
Yes.
If we use hydrological data to predict this. I think that based on bottom-up or top-down, I think hydrological data is the most important to use at step 2.
Perceptual model is something slightly different. We're thinking about our mental model of what causes what, right? So I'm failing the examination, so I do not get a job. I do not get a job, so I'm turning poor. I'm turning poor, so I cannot afford a car, right? A causal link of events. This is what a perceptual model is. So you have had this narrative, which was not linked so much, right? It was events, and it was sort of next to each other, but not linked. Now these items we have here, of your colleague, we now need to link them in a causative way. Maybe you can help, because you know the situation better. How can we, what causes what? What causes what? What causes what? This is the perceptual model, okay? We tried it, we're just trying to learn that. So it takes a while for us, please.
If I understood it right, I guess we should start with urbanization. Then urbanization causes increase in runoff.
Okay.
And we have, I think that maybe, I don't know if here in São Carlos is pollution is a problem.
Also in the last flood, Mario took pictures of the garbage full of trash, and it was clogged.
So it would be important to check how much of this flood is natural and how much is about pollution, because sometimes it increases a lot, the flood, if we have polluted rivers and the drainage system.
Yeah, so I guess the urbanization, and then people behavior, like about, I don't know, environmental education. They don't have a perception about the effects of their actions. Like they help to improve the flood. Like, and I don't know how can we simplify it, like lack of knowledge of population. Okay. I don't know.
Now the idea of these 7 steps is that in step 2 you do not need to solve the problems of step 6. We just leave them until later. We just solve one problem after the other. We don't have to worry about the data. In this simplified way, when you have more time, you of course look at the data at the beginning, right? But what we need more sentences of those kind that is on the whiteboard. Urbanization increases runoff. Runoff increases or decreases something else. This leads to something else, which leads to something else. We need a chain, a cascade of events, right? We need to work on that. Now, it's not so clear, right? It's just diffuse. And we need to pick this out. It's called framing, right?
I think we could put there population growth increase the pollution and increase the flood. Population growth. What else?
Urbanization, increase impermeabilization, land impermeabilization.
Can you say it again?
Yes. The population growth with urbanization increase the land impermeabilization. Impermeabilization.
Increases runoff. Yes. Good. Anything else?
Acho que também pode falar da retificação do rio, que diminui o tempo de
Yeah,
concentração.
Ela ia falar que...
Pode falar.
Não.
Não, pode falar.
You begin. We have enough time for everybody, please.
Straighten the river, because we had straightened the river.
I don't understand.
How can I say that? Straighten the river. Canalization increases, I don't know what, but I know increase something. The velocity.
Decrease the concentration time.
And increases the peak.
Yes.
Canalization increases the flood.
Thank you.
Yeah, velocity. Okay. Next. Yes. Okay, that's fine. We continue tomorrow. Okay, we do this 2 minutes and then I say goodbye. Yes?
Just in the first one, urbanization increases floods. I would say urbanization increases runoff, that increases erosion, and then it diminishes the volume, like the...
Increases erosion and
increases the siltation of the channels.
Siltation.
Yes. And then consequently, we have like less volume on the canals.
Less volume.
Yes. So you increase the peak.
Less floods.
Yes.
No, less area.
Ah. Increases floods through. Through siltation. Through siltation, right? Okay. What about effects of floods on people? The other way. Water on people. What about that? About the awareness in the shops? Yes? What's the causality here? More floods increase the economic losses. Okay, what else? It's still a bit random what we're doing here. Ideally, you would have like a chain one thing leads to another, which leads to another, which leads to another, which ideally like that, which is not like that yet. Okay? Well, we can try it again tomorrow. Okay? You can think about that. We try this tomorrow. Maybe also another example, see how we go time-wise. Okay. Thank you very much. And, well, you'll be around, I guess. Thank you.